section 8.3 is on the source-free series RLC. So again, now we have an L and a C in our circuit. Check on my microphone there. So let's look at how we're going to solve this. Let's do a KVL. I have this current I that goes all the way through because this is a series circuit. So my voltage here is I times R. Voltage through an inductor, L di dt. And then across my capacitor is V equal to 0. The voltage across a capacitor I know from chapter 6. Is 1 over C integral minus infinity to t I dt equals 0. So I'm going to take the derivative with respect to I and divide by L. So take derivative with respect to I and divide by L. So if I do that, and I'm going to rearrange a little bit, I get d squared I dt squared plus r over L di dt plus I over LC equals 0. So I need a solution for this. So I can try a solution of the form I equal a e to the st. All right, so I'm going to plug that in for I. And I get a, again, this is going in here for I, as squared e to the st, marker's doing something weird, plus ar over L s e to the st, plus a over lc e to the st equals 0. Now let's pull out an a e to the st, because that's our assumed solution. So a e to the st. And I get s squared plus r over ls plus 1 over lc equal to 0. And this is called my characteristic equation. Characteristic equation. So that's our differential equation or characteristic equation for from diff EQ. What are the roots? So I want to find our roots. We have S1 and 2 is equal to minus R over 2L plus or minus the square root R over 2L squared minus 1 over LC. And we can write this easier by using alpha and omega naught. Alpha is called our Nieper frequency. Omega naught is our resonant frequency. And we're going to write minus alpha plus or minus the square root of alpha squared minus omega naught squared. So we call alpha and omega our natural frequencies together. Alpha is R over 2L, and omega naught is 1 over the square root of LC. Okay, so we have 3 cases for this type of problem. We can have alpha greater than omega, alpha equal to omega, or alpha less than omega naught. And each case gives us a slightly different solution. 3 cases. And again, follow along with this in your text. Alpha greater than omega naught. If alpha is greater than omega naught, that means S1 and S2 are real. This is called our overdamped case. And please look in your text for a picture of what that means and what that looks like. That means we get an I of t that's A1e to the S1t plus A2e to the S2t. So A1 and A2 are just dummy coefficients. You can use A and B, you can use X and Y, I don't care. It doesn't matter what you use. But I've written A1 and A2. I think that's what the book does. Sometimes in my examples, I like to use A and B, just because I don't have to then drag around these subscripts. And at this point, I want to stop and note why we needed all those initial conditions. Because if we only had I of 0, that wouldn't be enough, right? That would give us this equation, one equation and two unknowns. We need a second equation. So that's where we use the di dt, initial condition, then take the derivative of this. Now we have two equations and our two unknowns, A1 and A2. So that first section feels like, why are we doing this? This is why you're doing it. Okay, our second case, alpha equals omega naught. If those are equal, S1 and S2 are equal to each other, and they're equal to alpha. So we call this critically damped. Again, look in your text at a photo of that. And our solution is A1 e to the minus alpha t plus A2t e to the minus alpha t. Third case is our most complicated one. Alpha is less than omega naught. If alpha is smaller than omega naught, you get a negative number in the square root. So S1 and S2 are complex. We call this underdamped. And mathematically, these are the most difficult ones to deal with. Circuits-wise, they're all the same, but we have to take a nasty derivative to solve these. So we want to define omega d as omega naught squared minus alpha squared. And now our solution is e to the minus alpha t times, I'm going to call it b1, cosine omega dt plus b2 sine omega dt. So obviously when you take this derivative, you have to do first times derivative of the second plus second times the derivative of the first. It just takes a little bit more work. So we will work some example problems in the next video.